So hi all, very good morning all. I'm happy to see you all this wonderful morning. So myself, Rahul David from Chippage Technologies. So today's event is about the significance of quality timing constraints for ASIC design. So like I heartily welcome our speaker, Mr. Pradeep. So about him, Mr. Pradeep has 18 plus years of experience in semiconductor industry. So currently he is working for ASDIA Inc. as a Director Technical Account Management for Asia Pacific region. So Mr. Pradeep holds a master's degree in VLSI system design from Conway University, UK, and a bachelor's degree in CE engineering from BITM. So Mr. Pradeep has worked on various aspects of VLSI design, fabrication, manufacturing flow like water processing, fab-related, chip-related manufacturing, design implementation, physical design, analog and mixed signal design flow, physical verification, RC extraction, and static timing analysis, STA, for the past few years. So now he is focused in timing sign-off and timing constraints domain. So I can heartily welcome Mr. Pradeep for this event, and I hand over the session to him. So Mr. Pradeep, please take it forward.
Thank you, Rahul. Thank you for giving this opportunity. So today's topic, as Rahul gave a brief introduction about it, the significance of quality timing constraints for ASIC designs. So yeah, once again, thanks Rahul for the introduction. And also I would like to highlight, I'm a alumni of Chippage also, because when I was working in the previous company, I had to upskill some of the, the technology, especially in physical design. So I joined, Chippage weekend course and did it. Okay, so yeah, I was saying I kind of enrolled for Chippage physical design course because in VLSI every field is very important. So I had to upskill. So I joined the physical design course a few years back at Chippage, and so that's how I know the Chippage Institute. So thanks for the opportunity, especially Venkat and Chippage team for this session today. Okay, so let me go through the agenda for today's session. So everything is timing and timing is everything. So you might be thinking why I am telling like this, right? So when I talk about it in the next slide, you will understand. So why timing is everything or everything is timing. And so we will have some generic understanding of constraints before we going into the timing constraints. Quick overview about a VLSI flow, because these constraints will be propagating towards the flow. And what all type of constraints are there, right, in a VLSI flow or ASIC flow. And timing constraints overview. Okay, so we'll be focusing on mainly timing constraints. So there are many constraints which goes through the design. So the focus will be on the timing constraints. And then I'll just give a quick intro about how we do the validation. And so I'm from a company called ASDIA. So we have we mainly work on timing constraint solution with a tool called Time Vision. So how we help actually industry to mitigate the challenges posed by the bad constraints and all. So that I just give a quick overview. So, and then some introduction about the multimode timing constraints. Then we can open for the Q&A. So everything is timing. Timing is everything. So this is a kind of a big statement, right? Actually, so why? Because if you see in the day-to-day life, so especially if you are watching a cricket match and then Sachin hits a 6, okay. So the commentator always tells what a sweet timing actually of the ball, right? So when the ball connects with the bat, actually with that timing it goes to 6 actually, right? So there we talk about timing. It's a generic term, right? Like, oh, what a timing actually. So it went to 6. So just imagine even a few delay or a few early of a shot, it can go anywhere actually. It may not go for 6. So that's the importance of timing actually. That's why, oh, okay, what a timing actually. That's a expression comes automatically. So similarly, like you are boarding a train and or a flight actually, just in time you are there basically, right? Just before closing the gate, or just in time you are reaching there. So again, like after boarding, you will be saying to yourself actually, what a timing, I didn't miss the train actually, so I caught it actually, or I'm into the airport actually before closing the gate, boarded the aircraft. So similarly, heavy rains, I think people in Bangalore can relate actually. So starting from April, it will start to rain anytime. So just before you reach, before the heavy rain, you reach the home actually. So you think yourself actually, right? What a timing actually. So I reached before the rain starts pouring. And then again, you are watching Sachin on 99 and power goes off, right? So you say like, what is this wrong time actually, right? The power went off. So it's in a way, in a day-to-day life actually, we use timing, right? If somebody is watching a comedy movie, they say, oh, the comedian has a very good timing actually, right? Or a comic timing. So timing is something like, that's why it's everything is and everywhere. So in life, how we talk about timing actually, right, which is an important aspect. Same thing in the chip also, So that's what the focus is on actually today. So constraints. So let us understand what is constraints actually without going into the technical details of it in a generic meaning actually, right? So the constraints is like something which limits basically, right? So we can think about it as a positive as well as a negative. So we will talk about both the instances. So if you are seeing this picture, so wherein there is a fish, within this bowl, fish bowl, okay. So the fish can grow only within this actually, right? That is a constraint the fish has basically. And what all the normal constraints we talk in day-to-day life, right? Financial constraints is one of the main thing actually, right? So everything will have a limit actually, or a budgeted basically. So that is one of the constraints. Then you have a time constraints. So you have to reach office before 9. You have to wake up at 5 o'clock or 6 o'clock. Actually, you have to drop the kids to the school, or you have to go somewhere actually in the evening before this time, or dinner this time. So you see there actually we already constrained actually from the morning basically, right? Without even knowing that, correct? So and then space constraints. Obviously, within the given space, you have to manage kind of thing, right? So that is one of the constraints. And then there is something like over constraint, and there is something like under constraint actually, right? So the best example for before I touch upon over and under constraint, let's think about practical usage of constraint. So you'll be at a traffic signal at the four sides, the traffic will be flowing actually, right? Just imagine if you don't have a signals, how it will be. It will be a lot of mess actually, right? So that's why each signal will have few seconds. So like three sides will be waiting, one side will be allowed actually. That will be like, that will be sequential. So each will be like waiting 60 seconds or 70 seconds, or if you are stuck at a silk board actually, even it may be more than a few minutes basically, right? So why it is? Because that is a constraint basically, right? You are constrained at the traffic signal, and it is necessary, because if you don't have that constraints, all the sides, the traffic will enter. It will be a big mess actually. Nobody can get out of that traffic. Okay, so that is a analogy I can give, like what is a constraint. Now what is keeping the same traffic signal? Let's talk about over constraint and under constraint. So over constraint is something like for something you need a more resources actually. Okay, and what means you're kind of testing your machine actually, right? More. So for example, if somebody is using a mixer grinder actually, right? So there is always a limit actually. They can do the some chutney or some batter basically. If you go beyond that, the mixer will not perform actually, right? Because it will try, the motor will rotate actually, but it's beyond the motor power. So it's kind of a over constraint. But in the same 1 liter mixer or 1 liter grinder, if you put like 50 grams of dal or something like that, that is like under constraint actually, right? The whole capacity you're not using. Okay, so that's why you have already always the constraints there also in the jar actually, right? You have to put something like this to get the optimal, smoothness in the batter or something like that. So it will complete actually. So that's where your over constraint and under constraint come in the picture. Okay, so as you can see, like different constraints are decisive for different situations, but the most fundamental constraint is limited time actually, right? So time is always a constraint for everyone. Okay, so that's about the normal constraints. So whether the constraints good or bad, it all depends on what is the where are we measuring actually. If you consider a situation of traffic signal, it is definitely good actually, right? Because if you don't constrain there, it will be a mess actually. And then if you keep time actually, I have to reach office like before this time or something like that. That constraint is good. So what is bad constraints? Yeah, bad constraints something somebody cannot meet that constraints actually, and they'll be in not a good state actually thinking about it. Okay, so that is a bad constraint basically, right? So constraints are required, okay, and how it has to be controlled or something like that. So that's what it depends on. It's very relative actually. So looking at the generic understanding, now let's look at the typical VLSI ASIC flow. Okay, on your left-hand side, as you can see, the green box, this is a front-end design, and then we have a back-end design. So in the front-end design, it's mainly, you have a design specification. So for example, somebody has to design an adder or, counter, so or a flop actually, let's say a simple example. And then you have a design specification actually, right? If it is a counter, how many registers are there, how it is connected, what is the feedback, all those things, what is the input, what is the output expected, everything will start with the design specification. And then we'll start with the RTL description basically, right? We write a Verilog code or VSTL code for the same design. So once we do that, the first thing is we have to do the functional verification. So when you say functional verification, so you are giving some inputs basically, and then you are getting the output. The output should be like expected as per the input. So that is a functional verification. So functional verification is something like you give all the vectors to the input and see like you are getting the expected output. So this is a front end. Okay. Now we have something like a back end actually, which starts with synthesis, because whatever you designed, it has to go to the foundry, right, for the tape out. Okay, so to do that, you have to convert your design to the whatever the technology given by the foundry. Let's say somebody is designing for 28 nanometer technology or 16 nanometer technology, so they'll be getting the the libraries from the foundry like TSMC or UMC or some other like Samsung or Intel. Okay, so they'll be porting their design to that technology. So that's what synthesis does. Okay, and then you have a netlist. All this while we are talking about the RTL, and now it is a netlist. So after that, so we have to convert into a graphical representation of this to send it to the foundry. So that's where place and route will come into the picture, wherein you physically, something like this is a logical implementation, and then there is a physical implementation. So you physically implement the things so that it will whatever the rules given by the foundry, you follow that actually, right? All the DRC rules, design rule checks, and all your design will be like a gates and everything will be converted into metals basically. At the end of the day, it will be metals of 7 layers or 8 layers or 11 layers actually. So based on that connectivity, so finally we give the graphical data stream representation, which goes to a foundry for taping out your design. So this is the whole flow, okay, of a VLSI or a SIG. So this is what actually on the right hand side you can see here. So there is a RTL, and then you have flow. But one thing you have to focus on is the constraints. You see here, the constraints is a seed which starts from the RTL itself. Along with the RTL, you have to supply the constraints, and then that constraints goes to synthesis. That constraints goes to STA, that is static timing analysis, and that constraints goes to the physical design. Okay, so that's why the constraints is very important here, because it is a seed for every stage of the design cycle. Okay, so coming to the what all the types of constraints are there. Design rule constraints. Okay, I will talk about it in the next slide with the details. So this is one of the constraints. Design rule constraints is given by foundries, because if you choose a 28 nanometer from TSMC, so then TSMC will tell, if you want your chip to be kind of fabricated in my foundry, you have to follow these design rules, and there is no waiver or there is no scope of negligence actually for this rule, because this rule is compulsory. You have to meet that, then only we can give the we can tape out in the foundry. The reason why means because people always question, in your foundry the yield is less actually. What is yield? Like if I designed like a chip basically in a wafer, let's say like means roughly we have 1,000 dies basically, right? So the yield will be like only like 40% or 50% basically, right? So this yield depends on one of the major thing is your design rule actually also, right? So if you don't have a proper design rule, the yield will also kind of affect. So that's why the foundry will always tell actually you have to follow this design rule constraints. So next is optimization constraints. This is mainly used in logical optimization or the physical optimization. And then physical constraints or a physical DRC. So, okay, so something like you have a DRC for the designing and then DRC for the physical. The timing constraints and the power constraints you have, like basically you have to make sure your power dissipation should be within the limits for the given design. So we have the power constraints there also. And then there is the DFT constraints, because post silicon will be testing the chip actually, right? So when the post silicon chip is tested, so there are some parameters the chip has to go through. Okay, so for that the DFT constraints are very important. So there is something like golden constraint file. So what is this golden constraint for, especially for the timing actually, right? So we will look upon in the next slide. But the hint is actually the golden constraint is something like this actually, right? Because when you start RTL, you will have some constraints to start with, timing constraints. So this is nothing but your golden constraint file, because that's where it started actually, right? And then that will be propagated towards the flow. So let's talk about design rule constraints. Okay, so this is basically required for design to function correctly as per the foundry. Okay, and then this is a library dependent. So what do you mean by library dependent? So when you say library dependent, it is like whatever the standard cell libraries I told you, right? The whole coding you have to change it to design actually. That is a technical tech node basically, right? Or a process node like 28 nanometer and everything. So the foundry will give the 28 nanometer library kind of thing actually, right? So that you have to port it basically, your design. Okay, so that's where we call it as a library dependent. So in the design rule constraints, so mainly we have three different constraints or rules basically, right? One is a max transition, max fan out, and max capacitance. So using this command like set max transition, max fan out, and capacitance. So basically there is a limit for input transition. It can't go beyond that actually. After that the cell will not function. Either the combinational cell or the sequential cell. Similarly, the fan out. A cell can drive only like so much of the fan out actually. Beyond that, it will have a degradation basically. So similarly for the capacitance. So because these two are very important for like the cell degradation. So then there is something like a minimum capacitance. So in the minimum capacitance, like max capacitance you have, right? This is the max load actually it can drive. Similarly, there is a minimum load actually a cell can drive. So these things, this is a very new thing actually, set min capacitance. Earlier, the focus was only on the max capacitance, but as the technology is shrinking, now we are talking of almost like 3 nanometer, 5 nanometer kind of a design. So the min capacitance also plays a very important role in the library. And then there are some optimization constraints. So as the name suggested, right, optimization. So what you have to optimize basically, right? Say in a given, with a given, the area of the chip actually, you need to meet the area, power, and the timing actually. And this, when you say timing is nothing but the speed. So for that, you need to do the optimization. How do you do the optimization? How do you tell the tool to do the optimization, right? So we have a different constraints, like for example, area. So we can tell the tool, especially when you are doing synthesis, saying that it should be limited to within this area, basically, right? Or even when you do the what do you say? Actually, the physical implementation, you can set that, and then speed or the performance, basically, right? So there, how do you supply? How do you know the design works at 2 gigahertz or 3 gigahertz or a 500 megahertz actually? So that's a clock speed actually, right? So that's what you set using create clock, and then IO delays basically to interact with the outside world. Okay, and then you tell that this path should be within this timing actually, right? That's where you use the set max delay and min delay. This is the optimization commands for the timing. And then for the power or the leakage, we have a different, like there are two kinds of power. One is the leakage power and one is the dynamic power. So leakage power normally happens during a standby. Like for example, if you charge your phone actually, right, and then keep it for 5 or 6 days without using it, it will discharge, to some percentage actually. So why? Because you're not operated anything, but it is discharging. That is nothing but your leakage power actually, right? Or okay, you can call it as a standby power actually. So that is one kind of a power. The second power is a dynamic power. So dynamic power is something like when you're doing some operations, this power will be consumed. So for example, you're playing a game actually in the mobile, or you can sending messages, or you are viewing the video. Okay, so that time dynamic power comes into the play. Okay, so these two optimizations we have to do. So for that we have different commands like dynamic optimization command and threshold constraints and the leakage optimization. This is the optimization constraints. So now let's focus on the timing constraints. Okay, so timing constraints, mainly timing is nothing but clock. Okay, a design is clocked actually, that is nothing but it's a timed. Okay, and then you have a input output path related constraints. Path optimization constraints basically similar to what we saw in the previous slide, and timing exceptions. So now the question is like, does clock latency matter during synthesis actually, right? When we do the clock constraints basically, right? So during synthesis, there will be no clock, right? So at that time, the clock latency will not matter much actually. So that will matter only when you start the physical design, wherein you start building the clock tree. It is called CTS. So what are the clock related constraints? So mainly, you have to define the clock. So when you say define the clock, let's say you're designing a CPU or a small IP actually. So that IP works for something like 200 or 500 megahertz. And if it is a CPU, it goes into the gigahertz actually, right? So you have to define the clock, and then what is the frequency or a period basically, right? So basically like you're defining like 1 nanoseconds actually, or like 1 gigahertz basically, and the waveform. So what is the waveform? When the clock has to form the cycle actually at the rising or the falling, so that you give as a waveform. So then we don't always, when we have one clock actually coming from the ELL, okay, so we don't use the same clock for entire design. Okay, so what we do is like, because certain logic of the design needs 1 gigahertz, but certain logic of the design needs 500 megahertz, 250 megahertz, 100 megahertz. So there we use a concept called divide the clock actually. So we have 1 gigahertz coming into the picture. What we do is we do the divide by 2. So that will go to some logic actually. Divide by 4, some logic. Divide by 10, some logic actually. So that's why we need a create generated clock. And then clock latency. This is very important because this latency is something like, which affects the performance of the design, because you don't get an effective clock because of this latency. That is like source latency and the network latency. We will touch upon in the next slide. Okay, so if you see here, this is a clock definition. You create a clock called sys clock name, and the period is 2. Okay, and the waveform is 0 and 1. So what we are saying to do is at 0 you rise and at 1 you fall. And sorry, you define it on the sys clock port. Okay, this is a primary port which is entering into the chip actually, and then this is a flop, FF1 flop. Okay, and then on this, if you see the waveform, at the 0 it will rise, and at the 1 it will fall, and then at the 2 actually it will rise again. So this forms one cycle, one clock cycle actually, right? So the period is 2. So 0 to 2 is what actually your clock is there. And now, this is a clock waveform basically for every cycle with a period of 2. Now I want to divide by 2, right? So I want to half the frequency. So then this is a divider circuit actually, and then this is a divided clock which goes out. And if you see here, so whatever the clock is there, if you divide by 2, that means whatever the one cycle of master clock will be having a 2 cycles in the divide by clock. If you see here, this is one cycle, like 2, right? And then now after divide by, actually it become like a 4 cycle, right? Sorry, the one cycle is become like a 4 ns. The period is becomes 4. So that becomes like a 2 cycles of master clock. So that is your clock basically. This is a basic clocking, which is required actually for the design. So now coming to latency, why latency is important? See, problem is you will be creating like one nanoseconds or 1 gigahertz actually, but the end of the day that 1 gigahertz will not come. So there is something like effective clock period. So, and then that is one thing, and second thing is this latency. The latency will impact actually the design. The reason is because if you take, this is a clock source wherein the clock is generating normally PLL. Okay, some people have an on-chip clock generator. Some people will have an off-chip clock generator actually. Okay, so the time taken by the clock from its source to enter the chip actually, or the primary port. Okay, so that is your source latency. So for example, here somewhere you have a clock actually, and then there is a path actually, and then it goes into the design. It takes like around 3 ns. Let's say that's the source latency. And then you have a clock definition point actually, right? So this is your master clock. This is your source actually. From here to here is a source latency. And then, the network latency is something like where the clock is consumed at the leaf level of the flop, and from the master clock definition. So whatever this clock network is there actually, right? There is a clock network you have a buffer chain or network chain actually. So that becomes like a network latency. If you see here, 3 ns and 1 ns will become total latency for this clock. Okay, now ideally we want the clock should function like a square wave, right? But in a practical condition, it is not possible. Okay, so because the transition is always like this actually. So this is what actually we were talking about the input transition and all, right? So this transition is always like this. So now you see the effect of latency. So my ideal clock is this. Okay, that is a master clock which is coming from the source. Okay, and now the clock at the register actually, right? So let's say here. So here the clock reaches. So it doesn't start from here actually. So there is a latency. Okay. So, and then you have something like, if you look at this window, okay, you have a rise time, the rise happens here actually, and you have a fall time, the fall happens here. And then there is a very important concept called uncertainty. Okay, so if you see this schematic actually, wherein you have a clock latency, and then you have the clock network here, and the uncertainty is like between these two actually, right? Now, what is uncertainty? So before we look at it, let's say when I have a clock of 1 gigahertz, so it will not come as 1 giga. The effective clock period will not be 1 gigahertz actually. You see here, this is my 1 gigahertz, but effective clock period will be something like 950 megahertz or 920 megahertz. The reason is the remaining time goes for uncertainty. What is uncertainty? it is to model the clock skew, which is what we are seeing here, and jitter, which is coming from the PLLs basically. And then there is something like on-chip variation. Okay, so on-chip variation is like there is a variation induced on the chip. Okay, because of that, there will be a difference in the delay. Okay, for both setup and the hold. Um, so that we have to model using on-chip variation. So all this will comprise of clock uncertainty, and then it is very normal in the industry. We have clock uncertainty defined for a given clock. For example, if you see this clock, there is a setup uncertainty of 200 PS actually. So if your period is like 1 ns, so you have to take out 200 PS in that. So that becomes your effective clock period will be only 800 PS basically. Okay. So now, if you did not understand what is uncertainty, so can we correlate uncertainty and the water tanker basically? So this is why water tanker, and then if you are in Bangalore or if you are in metro, you can always correlate with the water tanker actually. So what happens with the water tanker? So let's say water tanker is coming from a distance of some 10 kilometers actually, or 5 or 6 kilometers. You have ordered a one water tanker, and then he promised like 6,000 liters will be provided to you when we come to your doorstep. But what happens? You might have seen a common scene in the road. Um, the tap or some leakage will be there in the water tanker. So throughout the 5-6 kilometers, there will be one line of water actually, right? So there will be either a drop or some leakage actually will happen. And by the time it reaches and then put it in your sump or the tanks basically, right? It will not be 6,000 liters actually. It means there might be loss of 10% basically. Okay, so there might be like 200 or 200 liters or 100 liters would have lost in the road. So what is the effective water you got actually? So not 6,000, right? 6,000 minus some percentage loss. So that percentage loss is the uncertainty which we model in the chip. Okay, so this is very important because people are okay to be pessimistic in their design approach. They don't want to be optimistic because it will put a silicon into the risk actually. So that's why this becomes this plays a very key factor. So IO delay is something the block, what we say the block or the top level in the chip actually, right? It will interface with the outside world actually. So for example, if you see here, this is a design under test, and then there's a logic cloud, and this is outside world actually. So from here, that is from the input port to the it reaches here. The arrival time of the signal is 4 nanoseconds, and the clock period is 10 nanoseconds. So the input delay set is like 4 nanoseconds. So that means you, out of 10 nanoseconds, you need 4 nanoseconds. You give 6 nanoseconds to the outside world actually. So you have to confine within your this one with the 4 nanoseconds. So time consumed outside of the DUT before the data signal arrives into the input port. So for this, we have a commands actually, like first you have to create the clock, and with respect to this clock, we have a max set input delay, min input delay. Okay, so in this case, it's like 4 nanoseconds for max, let's say like maybe 0.5 nanoseconds for min. Similarly, the output delay. So only thing is now the output port actually will be interacting with the outside world. So then the output delay is like 4 nanoseconds. So this is the into reg, and this is the reg to out actually. So similarly, you have set output delay command actually, which will with respect to this clock. So for example, if you see like for a period of 20, I want to have a output delay. In this case, for a period of 15, I want to have a input delay. I just give a brief introduction about timing analysis because the session is not to cover the timing analysis, but it is good to know. So what is timing analysis? See, we saw the earlier in the flow wherein when you have a RTL, you have to do functional verification. So it does the functionality check basically, right? The adder works as an adder, counter works as a counter, or something like that. Now we need to also verify the timing or the performance of the design. How do we do that actually? So there are two methods basically you can do. Okay. So this is your input and this is output. You want to find the max frequency. So there is something like a technique called dynamic timing analysis. So dynamic timing analysis is a simulation based, wherein you have to give a vectors. You have to give a stimuli. Based on that, it will start the verification or the timing simulations basically, and then you will look at the results. But there are some limitations in the timing analysis, the dynamic timing analysis. The reason is nowadays the design size has gone to like a billion kind of instances actually. Number of cells. Very common is 100 million instance, 200 million instance, 500 million instance, and 1 billion instance. So for such a large design, the dynamic timing analysis will be very difficult because you can't generate so many stimulus actually and then allow the simulation time. So that's where static timing analysis is very important, because people call it as a sign off. So when you do the timing sign off, it should be from the STA tool actually, or static timing analysis tool. So you do the analysis of a design in the statistically, because why statistically? We are not doing any simulations here, and does not depend on the data value being applied at the input. Something like stimulus, it doesn't need. All it needs is a clock and the constraints. But yeah, each has advantage and disadvantage. Like for example, dynamic analysis is simulation based, more accurate basically, right? But static timing analysis is a formula based, algorithm based actually, and then it's more pessimistic. The problem with dynamic timing analysis is a slow runtime, but static is very fast. Okay, and again, as I said, the chip is very big. It's not possible to run the dynamic timing analysis. That's where you can do the STA. So for example, if you take any of the designs actually, right? So normally you have like Intel core, you have like AMD Ryzen actually CPU, and it is measured with a core actually, right? Either it can have a 24 or 32 threads combination or cores combination. Similarly, Ryzen also have like 6 or 12 core combination, and then you have something like a clock. So this is a frequency. Okay, so this is a frequency at which it can it can function. So all of you have bought like you have a mobile phone actually, right? So whatever the model you have bought, go to the GSM arena or some specification and look at it. So when they say 3 gigahertz or 5 gigahertz, okay, it's not the whole operation runs at 5 gigahertz actually. So there is a catch there actually. And when they say 24 cores or 16 cores, it's not that when you send SMS, it will work at 16 cores actually. So there is a range. You can look at it in the spec sheet. So they will say, so whenever there is a 8 cores, actually, this is a frequency. So when the 8 cores is enabled, only when you start doing some heavy applications like gaming and all, actually, till that time, the core will not be enabled, actually, right? So if you do just a normal WhatsApp or SMS or something like that, it will be normal cores and normal frequency. When the frequency will become high, because when you start playing games and doing heavy applications. Why that's so? The reason is, just think about it. It's all about power, okay, and it's all about speed actually, right? The speed and power. If you want more speed, you have to shell out more power basically. And battery is something like very important, correct? So even for SMS or even for small phone call and everything, if gigahertz start enabling, actually, just imagine what is the battery backup you'll get in the mobile phone. So think about it. Go back and then check your specification sheet, like whatever the mobile model you have. So you'll understand actually how it works. So, and if you see here, these are all the nanometer technology used. By why we have to use lesser nanometer technology? Because you can put more and more transistors or cells actually, because you can also put more and more functionalities, and then your area will be less actually. That's why you go for very small process technologies. And then total power dissipation will be there. For example, for this CPU, the power dissipation is 125 watt. Okay, so likewise you have for your mobile also. So, and then there are some constraints called timing exceptions. So what are timing exceptions? So there are some parts basically which is not real. It is not required to be considered actually, right? So just to give you an analogy, if you're in Bangalore, you might see a lot of dead ends actually, right, in the Bangalore. So it is not a way basically, it's a dead end. It's stopped there actually. You can't go beyond that. Okay. So something similar to like the false path also, you don't need that in the design. It may be through some static logic or something. It is required for some functionality. They have just kept it actually, but it don't have to be timed actually, right? So we can make it false path. Why we have to make it false path? So that is a question actually, right? If you don't make it as a false path, unnecessarily your physical design tools and STA tools starts optimizing or analyzing this actually, which is not required, and that leads to again area and power getting affected. So normally when we want to set a false path, we can set between these two different clock domains, I want to set the false path. That means any path from the scan clock to the core clock, I don't want to time it actually. So, okay, so I don't want to see the timing for that. And similarly, any path going through this mux actually, umux 0s, I don't want to time it actually. So that's how the false path works. And then there is something like multi-cycle path. So what is multi-cycle path? See, ideally, we want the design to work for one cycle. Means one clock cycle, it should work. That's how you get a better performance. But what happens is, since you are working on high frequency network, okay, and high frequency interface, the data needs some time to transfer. Okay, so instead of it can't transfer in one cycle actually. It needs more. So that's where what you have to do is you have to give a more time to data to arrive. So that's why you need to have a more than one clock cycle, like a MCP cycle 2. So for example, if you take this, you have UFF 0 and then UFF 1, and the up to 3 cycle delay is applied here, MCP 3. So that means your clock starts here the edge. So after the third edge, at the third edge, the launch will start actually, so that you are giving more time to the data to come in. So this is your path, and this is how actually you create the multi-cycle path 3. So for example, you have a create clock and then the clock name, which are 10 cycles. So multi-cycle path 3 means 3 into 10, that will be like 30 cycles. Normally for a 10 period, it will be like it will launch at 0 for the setup and then capture at 10 actually. That is the next edge basically, right? So whereas for the hold, it's the same edge actually, right? Hold is a 0 cycle edge. When it comes to setup now, it captures at the 3 cycles now instead of 1 cycle. So the edge will be at either it will be a 10, 20. So now, so far we saw the constraints, right? How it is applied. If you see the example, so let's say somebody is doing a logic synthesis or synthesis. Okay, so one of the step is like they specify the foundry libraries, and then they set all the design environment as per the foundry. Okay, and then if you see here, these are the design constraints or a design rule constraint. The design constraints is comprised of design rule constraints and design optimization constraints. So in the design rule constraints, you have a max transition, max fan out, and max capacitance. And design optimization, you have create clock and all the set max area, output delay, input delay, max delay, everything comes here. And then it compiles and optimizes the design. Okay, once it optimizes, it generates the netlist, and then we have to check the quality of the netlist. So this is typically where the constraints used. Similarly, similar constraints are used in STA mainly for the timing. So this is a one sample path, which this is start point, that is launching point is FF1. Capturing point is the data will be stored in the at this actually, right? FF2 basically. So that's where FF2 is a data, and this is a data arrival actually from the clock network. You see here clock network delay, and then so you have a path, and then it goes to data arrival time. Similarly, you have a capture day actually. That is data required time will be calculated here. And then the slack calculation happens basically. So in this case, the slack is met. Okay, that is nothing but timing is met. Timing is met, and there is no violation, which is a good news. That's what actually every STA engineer or a timing engineer will look at it. So be it a physical design engineer or a synthesis guy or a STA, so he will be looking at the same reports basically across actually. Just check there is no violation. This is a pre-layout timing report, because why pre-layout? We are not forming any clock tree synthesis here actually. Okay, it's not on the SPEF also. The spef is nothing but a parasitics which has to be back annotated to your netlist. That is not done here. This just after synthesis, we have generated the report. So if you see this report, so you have like the clock path, and you have that's a launch, this is a data path, and this is a arrival calculation. Okay, these are from the public domain. You can check it in any of the website. Actually, you will have a sample reports like this. Okay, so this is a launch, that is you're launching the data, and this is a capture or a latch. Actually, you are latching the data. Latching means you are holding the data basically. And then this is a combinational delay. It will go through that. Okay, and then this is a clock path delay. So the launch path plus the data path is a arrival calculation, and the capture path is a required time calculation. This is a slack calculation. So in this case, again, the slack is met because your data required time is 0. Okay, now, so constraints validation, why it is required. So we have seen the constraints, we have seen the timing analysis. Okay, now constraints validation, why it is required is you don't do constraint validation during timing. Actually, you have to do it before that. So if you remember the first slide wherein I saw, I showcased the flow, the RTL and the SDC constraints or design constraints were loaded, okay, into the simulation or into the synthesis. So there only you have to make sure the constraints are validated. So why validation is important? Let's talk about validation of generic. So if you remember early days, actually, right, when the checking was happening in the bus stand or the airport, the security used to check actually, each and everything in the bag, basically something like this, very manually. Okay, but as and when a lot of passengers started going in, and then they can't open all the bags actually and then see like what they are carrying, right? So then they came up with the automated way actually, right? So wherein they will scan everything, and then it will highlight actually if some weapons are there or something, some alcohol is there or something like that. It will highlight, and then they will segregate actually. So those are all kind of a bad constraints actually, right? So that's what that's how the validation is done. Now, why the validation again? So if you look at the farming, right, these weeds will create what do you say, the yield loss actually, and also it can infect the field. Okay, so now we have to remove the weeds basically, right? That's what a farmer does. Similarly, we don't want to have any silicon bug, because once the fabrication happens, and if you have a silicon bug, it's of no use actually, right? So you have to respin the if you have to respin the whole chip actually, and you will be astonished to see 20 to 40% of the tape out respins. Respins means you have to go back to RTL, open the RTL, to start again. Okay, it's caused by timing or clocking issues. So, or error in the timing verification specification are the majority issue. And you won't believe, per respin for 16 nanometer mask takes like $5 million. And for 7 nanometer, it is like $15 million. And imagine for 5 nanometer and 3 nanometer. Okay, so it will be like more. And any silicon bug, and you're not in time to market actually, right? So some company might miss like 100 million kind of dollars, basically the revenue loss because of the time to market. That's why it's very important. Okay, so that's why, so to validate this, we need a automation also, and then some quickly it has to catch. So that's where, just to give a brief introduction about what we do actually at OSDIA. We have a tool called Time Vision. So we focus on mainly the timing constraints, validation, generation, and management. Okay. So we are into the next generation solution for constraints management, like verification, integration, and the management. And now architecture is so massive that it can handle small IPs to big architectural chips, basically with 1 billion plus instances, 1,000 clocks, and number of IPs, several hierarchy levels, and the multiple mode support. Okay. So see, one of the main requirement for any constraints validation tool is it has to be quick, it has to be like fast, and the debug should be easy, and the learning should be also zero curve actually. If you're already using existing script for implementation, it has to be used there also, and then we have to continue. And then it has to be also noise free, because it's not the good tool which always gives like 1,000 or lakh violation. It is also a tool which should also kind of reduce the noise, because false violations you should not give, because again the engineers will go sit into there actually and then see whether the tool generated violation is correct or not. So those things the tool has to take care. Okay, that's what time vision does. And then debugging should be easy. So we have a one touch debug command. Actually, you just to do debug rule. Okay, it's a rule based basically, and then it will give complete details. So it's deployed in many of the top tier semiconductor companies. So typically, when you see how the constraints flow actually, right? So you have a RTL, you have a functional constraints, and then it goes to synthesis. And then after the synthesis or during the synthesis, you have a BIST DFT insertions, and then you have a test SDCs. And then that goes to gate net, that becomes gate netlist, and then you have merge SDC. And that goes to STA. Okay. So in STA, you look for some of the initial violations or a gross level violations in the STA. And then it goes to PNR. Then the final STA because it's a sign-off. And finally, the SOC handoff. Now, the problem is at each stage, you have a different issues. Like, for example, at synthesis, the constraints owner have missed some clock definitions. What happens when somebody has missed the clock definitions, right? If you go back to the schematic earlier I shown, so there was a sys clock which was going to some buffer, this one actually flop. Now, if you don't define the clock itself, this register is not active. The logic is missed actually, correct? It's not clocked. So similarly, in incorrectly defined generated clocks, and the case analysis is missing. Case analysis is one of the another constraints, and a missing IO constraints. If you don't budget it properly, then your outside world, if you don't budget the delay correctly, so then it will be a problem for the interface paths basically. And then in a preload STA, one clock will block another clock actually, and then you will be missing. There is something like a clock relationship actually, set clock groups. Okay, and the bogus timing arcs are seen. And then there is a half cycle path basically, and then somebody would have set up a set multi-cycle path minus setup, but set multi-cycle path minus hold they would have missed actually. So we catch that. So what happens is like, so these things people normally they kind of sit in the timing tool and then try to analyze it actually. And what they think is if you do the check timing or something in the STA, everything is clean. No, that is not true actually, because that will only certain aspects of the timing it will give, but it doesn't cover all the constraints issues basically. To go through each and every log, it will take long time actually. Its engineers will be wasting their time, and it causes multiple iterations, which also it causes the draining of resource basically, because when it comes to tape out, you have an army of people to put in there and then go through it actually, and then see what is the violation, how to fix the constraints and everything. Okay. So ultimately what happens is many constraints issues which is never identified and fixed will degrade the QR, okay, will degrade the PPA, and then it can also cause the silicon risk. So that's where time vision comes into the picture, wherein we have a check constraints, wherein we do the constraints validation. We have a 200 plus rules basically for each of the category. Okay, and each stage we'll make sure the constraints are checked, and then the constraints owner will go through that violations and then fix it. Yeah, so now comes to multimode. So what we saw is only one type of constraints actually, which is for functional mode. But if you see, this is a famous movie like Sanju, right? This is a different avatars of Ranbir Kapoor. Okay, so wherein one man, many lives, something like that. Your constraints also like that actually, right? So it's one design, okay, one chip, but different constraints actually. Like you have a functional mode constraints that will only take care of functional aspects of it actually, right? But there is something like a test mode for a DFT constraints. I told DFT constraints actually, right? So there you need to have like a scan speed, we'll say a scan shift basically. There is another mode, scan cap DC or scan DC. Okay, and then other test modes like BIST actually, memory BIST controllers basically you have to test, and the JTAG if you are using a JTAG in your design, okay, so that needs to be tested. So these many modes are there you need to handle, and then you need to verify. Okay, so with that I would like to say thank you, and before I go to the next this one, I would suggest you see we saw like how to develop constraints and what is the constraints background and everything. Okay, so I would suggest, because So many of you are students actually, and many of you are taking a course actually, right? And you'll be entering into the industry. One of the aspects you have to also look at it is like changing the habits, right? Atomic. This is one of the greatest books actually what we have today. This will definitely help you. So the courses will give you the knowledge actually, and this book will try to give you like how to change yourself actually to make it more efficient and more consistent. More good habits basically. So whenever you have a time, please try to read this. Yeah, with this, I want to stop the presentation. Yeah, so there is one question. Can you elaborate on process, how it is related in the design and derates? So in our design, can it be more than one master clock? Yes, you can have more than one master clock basically. Okay, so there are different clock generator basically. Okay, you can do that. And so derates. Um, so there are something like right now there is a technology called OCV was a very old technology. So right now you have something like advanced OCV. You have a POCV basically. Okay, so those things are there. So yeah, right now I didn't focus on timing analysis. It's more of a constraints actually, timing constraints. But when we take some session on the timing analysis, then we can always focus on delay, derates, and all. So how we know in our design has a false path? Uh, right, that's a good question. Like how you know the design has a false path. So there are two aspects. One is people do formal verification. Even time vision has that this one, wherein the tool will verify formally using a counter example whether the path is the false or not. Okay, but how do you know the design is false path? That's a design architect knows actually, because the constraints comes from them actually. They will set the false path or multi-cycle path. But what the tool will do is, whatever the false path and multi-cycle path you have set, whether it is correct or not. So that will be it will try to tell using the formal techniques. So in the design, do we do the multi-cycle activity or it comes from the SOC level? If we do, then what impacts is show in the constraints term. Okay, so as I said, how it is multi-cycle, it depends on the data path actually, correct? So if you have a long data path, you need to give more time for that the data to arrive actually at the capture flop. So for that, multi-cycle path is required. Yes, so many times multi-cycle path can be internal to the block or at the SOC level when it is interacting between two blocks basically, right? So that intersection path is called an interface basically. So there also you might need a multi-cycle if it is a high frequency paths basically. But having said that, just setting a multi-cycle path will not guarantee that it is a multi-cycle. You need to have a logic also. Okay, multi-cycle path to hold the multi-cycle path, you need to have a logic. So that is nothing but your pipelining stage in the RTL and everything. That has to be taken care. Just because I want 5 cycles, I can't put 5 cycles because the design has to take care of 5 cycles. That logic has to take care of 5 cycles. So that's why I told you, right, in the formally, time vision formal is one of the solution. It will formally prove whether the multi-cycle path provided for your design is correct or not. Okay, multi-cycle path, when change the edge of the setup or hold, the data has changed in the next cycle. See, always like that. When multi-cycle path you set n for setup and n-1 for hold. Why? Because setup always goes for the next edge actually, right? A rising edge, one because setup is what full cycle actually. So if you are given a 10, if you're given a 10 nanoseconds actually, for full 10 nanoseconds, it has to kind of time it actually, right? It starts at 0 and then captures at the next cycle or the next stage basically. That's how your setup edge happens. But the hold is like we are holding the data basically. It is on the same edge basically. It doesn't have a different edge. Now let's say you set a multi-cycle path of 4, okay, but you need to also make sure you set a multi-cycle path of 3 for hold. Otherwise, the hold will happen at the 0th edge actually by default. It will not happen at the 3rd edge actually, which it is supposed to happen. And such things also like it's a constraints issue. It's a bad constraint. Somebody has written set multi-cycle path 4 for minus setup, and they have not defined set multi-cycle path n-1, that is 4 -1 for hold. Okay, so that will be caught in timing analysis if you have not done the constraints analysis. So that's where the time vision will help actually. We have a rule actually which will tell that, you have defined for the home setup, but you have not defined for the hold actually. Okay, so it depends, like, not all the designs will have a multi-cycle paths, or we normally, ideally, in ideal condition, we don't want exceptions. It should, has, your design is good when you have a very minimum number of multi-cycle paths and false paths actually. Okay, that tells you the quality of design. For the multimode timing analysis, should we create a different SDC? Sometimes we observe functional and testing capture modes are merged. Which ones are recommended to merged or create SDC for different modes? Okay, now, okay, the idealistic scenario, we want to have a single mode actually, because people want to do single mode SDC and then do the sign off. But merge mode has become a need of R. The reason is you have a, let's say you have a 5 nanometer design. You have 5 modes, and then you have like 100 corners basically. So corner you can't optimize. But if you merge these 5 modes into one mode actually, so just imagine earlier you had to do like 5 into 100, that is 500 STA runs. Okay, so that reduces to 1 into 100, that is 100 runs. So you will be saving like 400 STA runs, not only 400 STA runs, 400 machines actually, right? That's why for a lower technology in the industry, people are moving towards the merged mode actually, because they can use the less resource. Okay, but ideally, single mode is always good actually, because you have a better control, because merge mode will have all the clockings and everything. You need to take care of it. But yeah, given the situation of right now with the lower technology, mode merge is very much required actually. So because you're not talking about one project, company will be working for 3 projects and each will have 10 blocks, and each block has to go through those corners basically, right? So that's why. During So why we always constrain 70, 30, 60, 40 IO? What is the minimum allowable percentage? What if even with the minimum allowable percentage also won't meet? So IO budgeting is very critical, and it is a nagging problem in the industry from long time. And 60, 40, 70, 30 is very pessimistic actually. Okay, because a path depends on your logic interaction, right? During what is the IO path actually? You have 3 sections basically, right? Into reg, top level, that is outside, and then reg to out actually, right? Reg to out, and then top level and into reg. So these 3 sections are there. Now, what is budgeting? So if a clock period is 10 nanoseconds, you need to calculate inside the block how much is required, and outside the block how much you have to give actually. Okay, so outside the block is at the SOC level actually, correct? Because it will be interacting with a different block. Now, 70, 30, 60, 40 may not solve your problem. It may be pessimistic most of the side, because people are okay to be pessimistic rather than optimistic, right? But there are some techniques now people are using is a delay-based budgeting, wherein they will check what is the delay from this register output to the input of the next register, and then they calculate like what is the internal path delay and then outside delay, and based on that they do the delay based computing, which is more of accurate compared to 70, 30 or 60, 40. Okay, but it is not like, you can't say that is optimistic or pessimistic. It will be realistic actually. Okay, so that is one of the technique. We also do that in time vision. We have IO budgeting. We do the SDF based IO budgeting, which does that. Otherwise, there are 3 types of budgeting: percentage based, okay, which is like 70, 30, 60, 40; logic level based. When you have a logic level, based on the logic level you can set, which is much more realistic than 70, 30, but still it is on the there we will take the worst logic as into the consideration, because you will have a number of paths more actually, right? It can go through any of the logic paths. The third is SDF based, that is standard delay format based or a delay based computation. So why do you always choose worst path? What is worst path actually, right? So let's say if you are looking at the timing analysis, okay, you have to make sure your chip works at the worst frequency. That is, a worst frequency is your best frequency actually, right? Because worst frequency is where actually you have to quote, because all the paths should be realized. What is the worst path is because that is a path which takes more delay. Okay, and that can be the critical path also. So that's why you need to make sure that you have to meet that first actually, right? Once you meet that, automatically the other paths will be also met. In SDC, only timing constraints will be there. Area and power constraints will also be there. Yes, so in SDC, SDC is a file actually, right? You can supply it as a tickle command actually. So if you see any, if you take a timing SDC, it will only timing related actually. But if you take a design constraints file actually, right, that will have both timing, area, and power constraints. So what is the difference between base layer and metal layer? So what happens is like you have like 7 layers in the design. Okay. So each layer will have its own, what do you say, actually the functionality. Like bottom 2 or 3 layers is mainly for the logic and the other layers are for routing. Okay. Now, what is base layer? Base layer is nothing but whatever the logic design you did actually, right? All the cells and everything. So that is fabricated using base layers. And then the routing layers will be used. So when it goes for tape out, actually, the tape out will have first base layer actually. So that's why in industry, there are two different stages of tape out. One is a base tape out and one is a metal tape out. So base tape out is something like, most of the logics and everything will be fabricated there. Okay. And then most of your routing is also done. Everything is there. Okay. But if you get some functional issues or not a functional, like minor issues wherein you want more time to fix it, what people will do is will take the window of 3 weeks from the base tape out to the metal tape out. Within this period, what they will do is they'll have something like a spare cells. The spare cells can be a combo cells actually. They will start, connecting those routing layer to that actually, based on, whatever the incremental fix they want to do, and then goes to metal. Once the metal happens, metal MTO, that is called a metal tape out, that is your final tape out actually. So what role AI plays in the VLSI field? Yes, it plays a lot actually. See, there are two parts basically. I represent a EDA community. If you talk about EDA community, there are many tools actually, which is ML or a machine learning enabled or AI enabled. Okay, so we are also working towards that. The reason is so since you run, it's a production runs actually, right? If you take a company like Qualcomm, Intel, Samsung, a lot of chips will be coming out actually, and then there are some parameters basically, so we can learn it actually, and then automatically it can be used. Like for example, for certain design, this is a machine performance, this is a memory required. So all those things you can use AI as a utility, and both the design side and the EDA side, and it can be useful. Definitely useful, but till what extent we use the AI, so those things has to be kind of taken care. How do we miss timing even after taping? Does not STA report all the failed timing paths? See, failed timing paths doesn't guarantee you, everything is fine actually, right? So normally people do GLS, gate level simulations, okay, before the tape out or something like that. So that will catch any of the other constraints issues. So it need not necessary that all the whatever the timing, if everything is met, also there is something. No, because I told you, right, one of the case wherein somebody has missed clock definition itself, that STA will not tell you. Okay, so that because it comes as an unconstrained path, and then you have to look into it actually, and unclock flop kind of thing. But okay, but one clock blocking another clock actually, so that STA will not tell. That is only caught in sometime in GLS actually, right? That's why we are saying constraints issues has to be fixed before the STA. Of course, STA is a sign off, okay, for some other reason, like for the timing and everything. Okay, but that doesn't guarantee that everything is fine actually. So otherwise, people wouldn't have done GLS actually, right? Can you elaborate on DFT constraints? Yeah. So DFT constraints is nothing but test mode constraints actually. So timing constraints, you have a functional mode and test mode. In the test mode, you have like a scan at speed. Scan at speed means it works as a functional, but at the scan path, you have two paths actually, right? One is functional path with the functional clocks, and then test mode path with the test clocks basically. So you have a clock mux basically, which controls the propagation of the functional and the test clock. So something like that. So that we call it as a DFT timing constraints. Yes, you can. So basically, our recommendation: can you use the time vision for chip top post STA timing SDC validation? Yes, at every stage you can use it, and you can start at the RTL level. That's where you have to start the constraints cleanup or constraints validation from the RTL to the all the flow actually post synthesis, post pre STA, and post PNR. How to know the input delay value of the primary port? Yeah, you need to check the path basically, right? And then you'll come to know like what is the logic level. And so that's how you have to do that. SOC design structure, which are the basic elements to be considered. So SOC design structure, you see, like it depends, right? You want to go for tile-based flow or the, kind of abated flow basically. So if something, you don't have much of a logic at the SOC, people go for abated flow. But if you have some clock logic or a clock generator, you have separate, like you have a hierarchical, but it is not abated. So mostly it is a hierarchical approach only, because flat approach you can't have it actually, because any tool will not handle the such implementation and everything. So you need to partition it with a hierarchy basically, and then you have to do it. In a timing report, what we can expect the behavior of the design for positive or negative slack. So when you say positive means, the data has to be arrived before the clock actually, right? For the setup basically. So when you have a good positive number for the slack means, so your data is having a very good margin actually. So you'll not miss the data. So that is what you'll get. Negative means definitely you will miss this data actually, right? Nobody wants to do that. Whenever you have a negative slack, what you do is you do the ECO basically and try to fix the path and make sure it is a fixed path is fixed. At the SOC level, what is the budget usually? See, at the SOC level, there is nothing like budgeting, because SOC is something like a chip which goes and sit on the system or the PCB board. So there is a different IO package IO actually. So that is different. So that we don't usually model in the timing constraints at the SOC level. Yeah, how will identify false path? I already answered this. In case if we have a latch to the output path, do we need to fix these kinds of path as well? If yes, how do supposed to? So there is, okay, so the latch path is always called as like, the latch is used mainly for the high frequency designs actually, right? So that's what. So now if you have a latch at the output path, okay, so when you say, do we need to fix it? It all depends on the path, right? What is happening, where it is coming from? Are you seeing any violation? So depending on that, you have to fix it. Can affect, no, so it's not necessary, because everything cannot be done by AI, right? You need engineers also for many of the things. So if that is the case, actually, if EDA also does everything AI, I can't tell that I will lose my job actually because AI will handle it actually. No, it's not like that. So definitely what it will do is it will help actually. I think it is more of a complementing solution, not the conflicting. So when and why define set annotated delay, set annotated transition through nets delay, and taking from SPEF. And okay, so what happens is set annotated delay. Normally people use SDF actually, right? A standard delay format, which is generated by the tool for the simulations. And now for some of the nets, they might not have that actually. So they will use this set annotated delay. And even the transition also actually, they want to override some of the transition coming from the library or something like that. They can do the set annotated transition. So SPEF mainly gives you the capacitance, right? That is RC kind of value. Okay, so that is your interconnect. Interconnect. This one actually, the parasitics basically, which is coming from the SPEF.
Okay, so before we go into like what career opportunities you have in semiconductor industry, let's see like about the chip edge. So we are basically a skill development company or VLSI EdTech company. So we founded in the year 2012 and we are managed by senior industry professionals. And we are like 11 plus years of experience in VLSI training. We have trained more than 4,500 engineers. And we have 200 plus hiring companies who will be hiring students from us after they complete their program. And the best part is we give like 100% placement support for the students who does programs with us. Okay, coming into the course models, we have VLSI weekend courses, VLSI job-oriented courses, on-demand, which is self-learning courses, and VLSI multi-semester certification courses, and internships for students from third semester to eighth semester. So the weekend courses are totally live online, and job-oriented VLSI courses are totally offline. So on-demand self-learning is also online. Multi-semester and internship programs will be either online or live online. So these are our VLSI program offerings. We offer programs for students and freshers, and we offer it for professionals, we offer for enterprises, and also for educational institutions. So for students, we have integrated internship model. For professionals, we have the entire digital and analog VLSI design circle through weekend classes. For enterprises, we have custom-based courses for both freshers and laterals. For educational institutes, we have train the trainer programs and also certification programs for students delivered in college itself. So coming to the self-paced VLSI programs, we have self-paced VLSI in these domains: design for test, ASIC design, verification, RTL design using spyglass, and also physical design. And these are our recent courses. We have RTL design, design verification, design for test, physical design, synthesis and sign-off STA and LEC. And we have upcoming courses such as formal verification, TCL scripting, and Python scripting. So these are our courses offered through weekend classes. We offer courses in RTL design, design verification, formal verification, design for test and physical design. And the mode of training will be completely online, and the duration would be 5 months, and industrial trainings on weekend sessions would be from Saturday and Sunday. So who can join? Working professionals, students. For them, we offer hybrid batches as well. For students, the batches will be kind of hybrid, weekdays plus weekend classes. So we have one upcoming course on RTL design on 2nd March 24 and formal verification on 16th March 24. So the next course is VLSI internship and certification courses for students. So the internship program would be like 4, 8, and 16 weeks of internships. So VLSI certification, we have for the students who are currently doing their third semester, they can take this program and start it from their third semester till eighth semester. For every semester, they will have from 40 hours to 60 hours of training, and they have integrated internships, which is already combined. And also, there will be a project given to the students as well as placement assistance in VLSI companies will be provided after the successful completion of the program. So we also have short-term job-oriented certification courses. This will be a 6-month offline program with integrated internship with placement assistance. So next is, this is our offline job-oriented programs. So we have physical design and design verification. Both will be a duration of 6 months. And this has a 600 hours of interactive learning, assessment after every module. And the best part is we give placement assistance, and also we have no cost EMA as well. So VLSI certification courses for students and freshers starts, physical design starts at 19th February, and design verification also starts 19th February. So whoever who are interested to join this program, you can always register through our link, which is available at the chat bar. So mode of training would be classroom as well as offline. So the duration would be 6 months, and industry trainers on weekend sessions as well in Saturdays and Sundays. So for who can join, the joiners can be graduated freshers as well as 7th and 8th semester of BTech students and first and second year of LTech students. So admission process will be an online test and a technical interview session. So from this online test and technical interview session, you can also avail for this partial scholarship, which would be like 40 to 60% of scholarship on the whole fees. So the course highlights are: this is an integrated internship with certificate, instructor-led live online classes, comprehensive placement assistance, course designed by industry expert, industry relevant projects, mock interviews by industry experts, and no cost EMI. So the integrated internship is integrated with courses that are 2 phases. One is phase 1, learning, 5 months, learning representative domain knowledge in 5 months, as well as phase 2, application of your learning in projects. One project will be part of your coursework. Second project as part of your internship. So no extra fee for internship will be collected for this model. So placement assistance, we understand that you will be investing your money, time to acquire the skills required to get your job in VLSI industry. So till you get a job, there will be 100% placement support given by our placement team. So we have 200 plus hiring companies who we are partnered with. So after the completion of the program, you'll be sent for interviews and to these companies, and they will start hiring you once you start completing your program. So soft skill training and mock interviews will be given at the end of your training, and mock interviews will be performed by industry experts and professionals. So these are a few of our hiring companies. As I said before, there are 200 plus hiring companies we have, and these are a few of our hiring companies. We have HCL, TCS, Intel, and Cadence as well. So this would be our partnering company. We have Celton, which is our services companies, and we are partnered with IESA, which is the Indian Electronics and Semiconductor Association, and we are an EDA partner of Synopsys, which is like all the programs shown above will be taught to you using the Synopsys tools. How this model works. So you have to apply for the course, attend the written test, the technical interview, and 100% scholarship candidates will be announced. And remaining candidates can join availing special discount, complete the course and get certified in VLSI, attend the placement opportunities in VLSI companies, and get placed in VLSI companies.
So yes, that's it. Thank you so much, Mr. Pradeep, for giving us this wonderful session this morning. And thank you so much for all the participants who came their time and effort for this event and made it a very successful event. So like going forward, we'll be having this kind of events every month. So those who are interested, you can register through our website and you can subscribe our blog pages. And thank you so much, everyone, for joining this event. You have a wonderful day ahead. Thank you. Thank you so much.